first Regis Professor, new Professor of Materials at Manchester University. He's also Chief Scientist at the Henry Royce Institute for Advanced Materials, and his title is Materials 4.0, Accelerating Innovation in Materials Discovery and Manufacturing. Phil.
Thank you. Thank you very much. It's an interesting journey through the history of priorities, if you like. If you look at Regis Professors, if you Wikipedia it, it's really interesting to see what they prioritized 500 years ago. And it's good that at least 500 years later, they have decided materials is worth having a Regis Professor. So, it is interesting. I would like to build on a lot of things that have been said already, and I'll try and skip through some of the things that maybe resonate with the things that you've already said, and move on to perhaps some of the other elements. But there we go. So for those of you who don't know, the Henry Royce Institute was set up in 2016, and I think it's a low TRL activity, and it's about building on our excellence in advanced materials. And I guess my message to you is that the Royce is not just an institute, it's not just a hub, it should be about a community. And I think it's really important to come today and talk about the future of metallurgy, because that's integral to what we're trying to do. And I hope everyone realizes that the Institute is not a building, it's about the community in the UK. And I think it's really, really important that we get together and tackle some of these big challenges, because they're global challenges, and it's only by working together that we've got any chance. And as I said, it's scattered around the UK. I'm not going to spend too long on this image, just to say that, we have facilities all across the UK, and anyone in the UK can get access to those facilities, whether they're in academia, whether they're in industry, whether they're in RTOs. And we have a particularly good mechanism for students to travel and use facilities, rather like you might go to Diamond to use a facility and you learn a lot. I did all my early days going around international facilities, Denmark, France, America, and the UK. You learn a lot by doing experiments with other people, and the Royce is about people coming and using our facilities. So if you have students who need access to facilities, Royce is there. Right, building on the things that Dan said, I don't really want to go into this, but there is this cakeism thing, and it was in the paper yesterday, an article about cakeism, actually. Britain is very much about cakeism. We want to have all the things we want, but we also would like to meet all these goals. And we really need to start having adult conversations about where we want to go, because graphs like this, we keep putting this back and back and back, and we certainly don't look up. We just get on and assume that we can have our lifestyles and we can do the things we want to do, and somebody at some point will sort the problem out for us. So these graphs are getting scarier and scarier, and maybe some of the evidence is getting more and more real. And we're already well behind where we want to be in 2050. As Jürgen said, if you want to get to there, I wouldn't start from here. We've got some big challenges to meet. And I'm not going to dwell on this one or the next slide, because they basically say the same things that Dan said. We really need to understand materials. Cement is a massive challenge. I think it's. I think it actually. The figures I have are even more frightening than the ones that you showed, actually. But steel, aluminium, cement, these are big generators. And again, this is just a picture with 1 kilometer on this scale. If you look at, you showed the images for aluminium. You look at what it takes to recover platinum, what it takes to recover some of these really rare materials. It's not just the amount of energy. Something like 8% of our energy goes into recovering these materials. 8%. That's just taking big pieces of rock and turning them into small pieces of rock, essentially. So we really do need to understand this, and we need to understand the amount of water that is used to recover these materials. So we need to start looking not just at recovering metals from the ground. We need to think about recovering metals and recovering materials from the products we make, and simple things about designing. You reminded me, Dan, of the challenges. I went round the in Manchester is all about cotton. I went round the cotton mills. And the cotton mills, in the old days, what happened was all the young boys didn't live very long. They were orphans, generally, working in the cotton mills. And one of the things they died of was the fact they sucked in cotton. Why did they suck in cotton? They sucked in cotton because when they had to thread, this thing that used to go backwards and forwards, to thread it, they would suck it, to suck the cotton through. And they were getting all this cotton fibers into their lungs, and they were dying. somebody said, you can't do this anymore. They banned this approach. Within a very short period of time, somebody invented a way of threading cotton that didn't require boys to die. Now, we have to understand that innovation is driven not just by bright minds, it's also driven by legislation and policy. So I think it is really important. And why is it that we have a system where you can't take your phone apart, where the phone isn't designed to be recovered, it's designed to go in the bin and to make it into landfill? We can redesign how we build phones such that you can take those materials and recycle them. We have to start in design. It's not just about education, it's about design, and design for recovery. So we have a long way to go. Picking up on what Diron said, is that manufacturing is a big element of our net zero commitment, and most of it doesn't take place in the UK. We do most of our manufacturing now outside of the UK. So we need to understand our responsibility is not just on our shore, but overseas as well. And we need to think about maybe we should be reshoring some of that. And if we don't take account of that, then we will end up actually accelerating the problem, not meeting it. Again, this came from the catapults actually, but it's just a diagram that shows where is the carbon footprint. And much of the carbon footprint, I've got ones for the steel industry, automotive, aerospace, and so on. But the message is largely the same. A large fraction of our carbon footprint comes in the primary materials and their processing. So we need to understand that process, and we need to remanufacture that process. So, if we will not simply get out of our situation simply by tackling this end area. We need to understand raw materials, materials processing, and materials reprocessing. So it's really, really important at that end. And so materials. I mean, when I was a kid, material science was all about Concorde. It was about going to the moon. Really exciting projects. It's really now about planet Earth and what we do. And I think there's never been a more important time to be a material scientist. The challenges are really significant. So time is not on our side. I mean, it often takes 10 to 20 years to get new materials into practice. So if we're not careful, meeting 2050 is basically based around the materials we have today or in the pipeline today. We need to move forward, and we need to change the approach to the development of new materials, and we need to accelerate that change. So I wanted to just, my message today, I guess, is all about how do we take forward some of the things that Brian mentioned at the beginning about the opportunities that we have, and I would argue that there are three really important elements to creating a faster innovation economy. One is small-scale experiments, and I always Diron said about practical knowledge. I think it's interesting now, we've forgotten the physical twin. We focus on this digital twin, but actually the physical twin is really, really important. We need to think more carefully about how we do that, because, I mean, from your early days in modelling any phenomenon, when you produce a model, it's rubbish. That model only becomes better when you add in information. And a little bit of information makes it a lot better. And a lot of information can make it a lot better. So we need to think more about small-scale experiments. How do we? A common term now, I think, is fail fast. How do we fail fast? The second point is about computational tools, and the third is digital data. So how much of our data? I know from experience, many of my students, their data sits on, I'll say, a floppy drive. That just shows how old I am, but you understand the point I'm making. It sits in private spaces, and that data is essentially hidden from the world. How do we make that data available? So we need to. I think that we have a perfect storm in that we can do all three of these things very quickly. And the Royce, our facilities are very much focused on these small-scale experiments, doing things more quickly. And I think this is the really important aspect we need to think about as we go forward. So if we take them one at a time, I think this is a traditional processing microstructure performance. I don't think that has changed. I think that's still as important as it ever was. But we need to think quickly about how do we completely re-engineer this process, to accelerate that process, and also to make sure that the information, the work that's being done here in Brunel, for example, is connected to the work that's being done in Manchester, that's connected to the work that's being done in California, etc., etc. Because, as we said, it's a world problem. We need to take that information and use it. And this is just an example from the chemical formulation side. But this was an 8-day experiment where the robot travelled 2.2 kilometres, doing 700 experiments and making a huge number of formulations. So this is a very important approach forward. And whether we're processing metals or whether we're processing chemicals, I think we need to digitise. We need to get the data from the process much more integrated so that we have a solid foundation for the modelling work that we want to do. Can you forward the slide? Yeah. Similarly, we need to accelerate the characterization side, and whether that we have a huge opportunity. Whether that's going to diamond light source, whether it's going to other advanced facilities, or whether it's in the lab, we need to think about how do we collect all that information much more quickly. How do we collect low-level information? I mean, for example, if you're making coatings, we should be able to make thousands of different coating formulations, and we should be able to use small-scale tests, whether that's hardness indents or whether that's grazing incidence, X-ray, to try and collect the information we need to iterate much more quickly than we can do at the present. The second thing is we need to think about how do we store all that data. And I sometimes use the term Internet of Materials. I think that there is an approach that says we should formalize everything we record in one big sort of Excel spreadsheet, and we should fill that Excel spreadsheet. I suspect that's not the way we will go forward. Probably the way we'll go forward is through a network of databases. So we may end up with a mass of different databases, and then I guess the real skill is being the Google of that space. How do we scrape that information from all those different data sources? How do we then bring it together, validate it, identify what data is reliable, identify what data is appropriate to a particular situation, and then allow it to be fed into modelling, and to manage all the IP and the ownership and the citations issues and so on. And some of the data is not easy to digitise. We talk about fingerprints here. I'll come back to that in a minute. But obviously these FAIR principles, the data must be findable, accessible, interoperable, and reusable. And I think we spend all of our attention on the database and very little bit on this end. I use ResearchGate a little bit. Why do I use ResearchGate? I use ResearchGate because when I look for papers, I don't find them in journals. Often ResearchGate throws them back at me and says, oh, there's this paper. Then I have to go and find them in the journal. We need to focus on how do we make sure data is reused, because if it's reused, people will store it. And we spend all our time trying to tell people they've got to store it. We don't think enough about how we make it available and how we make people get benefit from that, because it's all about culture change. Okay. So then the final part of that is really about digital systems. So yeah, just as we have fast make, fast test, and fast characterize for the physical twin, we need to think very carefully about the digital twin. And the digital twin is really about microstructural models, it's about materials models, and it's about process models. And of course, a lot of us have been working in this area for many years, but we need to couple those so that we can make this whole process work more quickly. And I won't go through that. I'm sure you're all aware of the various paradigms and this move to data-driven science. I'm not so sure. We tend to think of this as one replacing the next. I actually don't think, it clearly isn't one replacing the next. There are places where we need empirical models. Harry made me laugh about a joke this morning about Hall-Petch. Very, very useful empirical model. And I'm sure he'll tell the joke later if somebody asks him. It made me laugh anyway. There's a paradigm-based theoretical science, clearly really important, computational models, and of course big data. We need all of them, and we need to work out how they work together. I think this is an interesting example, really, which is the Genome Project. I don't know if you went on the Materials Project today, it would probably tell you how many new materials have been proposed. It was 130,000, I think, when I looked, and that was a few years ago. Now, in one sense, that's a great testimony to our computational capability. But the big question is, if we've invented 130,000 materials, where are they? Where are all those materials we've generated? They've been mostly generated in silico. And of course, the other problem we have is that it's a bit, you talked about cookery. Actually, just because you have the ingredients doesn't mean to say you know how to make the cake. Making the cake is really, really important. So just because you can predict a unit cell doesn't mean to say you can make the material. As we know as material scientists, microstructure, defects, processing, these are all really, really important and really big challenges. So I think, whilst this is very, very exciting, we need to think that in material science it's more complicated. It's more complicated. In fact, Cedar said, he started in material science, realised it was too complicated, so he moved into chemistry. I'm not sure whether that was just to make material scientists feel better. But I do think it is true that we have a very complicated problem, because we have to understand microstructure and we have to understand processing across a very wide range of scales. So it is a big challenge, but it's one that we need to tackle. And of course, microstructure is critical to what we do at all scales. And we need to think about how do we capture that, and people like Liz Holm in the States have been working on that. I sometimes call it a microstructurally cognizant digital twin. And we need all these different models, and we need all these different observations. And in some cases we have firm fundamental equations. In some cases we have numerical models. And in some cases we need machine learning to join these different length scales together. So we have a really big opportunity here. We have all these wonderful techniques, from the TEM through to X-ray imaging through to a whole range of other measurement technologies. But it's only really by understanding this across all the length scales. This is an example taken from fusion, of course. We need to understand defects in fusion right at the atom scale, how defects accumulate to form helium bubbles or whatever, how those interact with dislocations, how that affects plasticity and so forth. So we need to understand all of those things if we're going to succeed. And we need to be able to understand what are the most appropriate length scales for a given process. Okay. So metallurgy is 150 years old. Sheffield Sorby was probably the first person to collect microstructures. And even today, we have no mathematical form for describing that microstructure. We need to develop ways of digitally fingerprinting microstructures so they can go into those kind of models I was talking about. So just a challenge, I think. One of our challenges, how do we start to input these kind of microstructures, or the variety of microstructures that we have? How do we, clearly it's very important. You just look at this bottom image with different types of cast iron. The microstructure is really important. How do we capture this and input it into models? And of course, the data can take all sorts of forms. It can take information about crystallography, chemistry, and so forth. So we need to be able to put all of this microstructural information into our learning. And how do we capture that? So that's a really important point. And of course, we need a digital thread through the whole of the process. So that's another one of the problems, that the product you end up with is actually a bit like people. People, you see the person today, but they're the consequence of a lifetime of experiences. And material science, it tends to be the same thing too. You need to be able to understand how far back in the process chain do you need to have to go. How do you connect those up? Often we think about them and we say that if you cast it, it has to have a certain grain size, and then you form it and so on. We don't think about it in an integrated way, and so some of the specifications may be over conservative. They may be unnecessary. They may be adding extra price into the process. So we need to do this more holistically in a more joined up way. And obviously integrated computational materials engineering is one of them. And you can produce maps of what you need to do. This one came from the advanced metals processing activity within the Royce. But this is a really exciting place to be. A really exciting place to be. There's lots and lots of things to do here. And I'm just going to just take a little bit more of a wider look as well, because it's about future of metallurgy, to think about digital threads and materials passports. We need to build up these structures and understand how to link together what goes on at the different length scales, at the different time scales. And yeah. So look, this is just an example of how we might go forward. And again, it picks up on Duran's point about stewardship. And if we don't measure, the reason your Norwegian wanted to buy a certain car was because you can measure it. When people now go in the UK, they buy a fridge, and that fridge has a whole series of grades on it, and they can make a decision based on that. When they go into Primark or they go into a plush fashion house, they don't know how much of that material science is leading to sustainable materials and how much of that is based on sweatshops and terrible chemical processes and so on. We have no bars to really measure that. Likewise, we have no bars on our material. When you buy your cobalt, you don't know where that cobalt has come from, or the cobalt that's gone into the products you buy. You don't know what kind of processes have been used. So I think materials passports are really important, and we're going to have to start focusing on those. I just took this from the London Metals Exchange passport, and that now includes a whole range of things about carbon emissions, biodiversity, recycling, reducing, and mitigating polluting activities. So we have to measure these things. If we measure these things, we can start to make choices. And if we make choices, it's going to be more expensive, but at least we might make the right choices. Social considerations clearly critical as well, and obviously elements about good governance and so forth. So a really exciting opportunity. And I just you mentioned again, Darren, you mentioned a point about leasing. Well, maybe we should be, and I was doing some work with Anglo-American, and there is now this idea that actually we won't own the metals in our phone. We will lease them. So basically the companies will lease those materials. Those materials they will then pay back at the end of life. So it's not just about, maybe leasing your car or leasing the product. You may actually lease the materials that lie within the product. And therefore, that would change the economic model. So, resonating with the things that were said earlier, what Brian said about and, if we're going to create that circular economy, my gut feeling is we need to think very carefully about how we do that business. The current business linear model isn't going to work. We have to create a circular model, or in fact, a series of circular models with different levels of so we'll have recycling, we'll have reuse, and so forth. We need to think of those circles economically and how we're going to make them work. So that was really my final point, was maybe in the future we will be leasing our materials and borrowing them, which is, I don't know if sometimes when I fly through Swiss airports, it talks about, you don't buy a watch, you kind of look after it for the generations. Well, maybe that's true about materials too. Maybe you don't buy an Apple phone, you buy materials that you should be looking after for the future generations. Maybe that will change in the future. Okay, so just to take that diagram that I showed before, the other opportunity that we have, I think, is to take data from life and put that life back into those models so that we understand from production experience. So that, for example, if you have an aircraft aero engine, and that aero engine is flying to South America on regular trips, maybe you don't replace those parts as regularly as if you're making trips to, let's say, to Shanghai via Dubai or wherever, where the pollution and the sand and so forth will degrade those materials much more quickly. So maybe by understanding, through inline sensors, service data and monitoring, that we can actually prolong the life of materials as well. Okay, just one quick point. There's lots and lots of data on the Henry Royce Institute website. You'll find a whole series of reports on Materials 4.0 there. We're really trying to move this forward. And just one other quick thing. Royce is going to set up a CDT in Materials 4.0, and we're bidding for an AI hub in materials. And again, I wouldn't regard that as Royce bidding. I would say that's a UK thing. So if you're interested in joining the AI hub for materials, if we get through the first round, please come and speak to me. We're really, really keen. to do so. So just want to finish by saying I think that the future is really exciting. Exciting in some good ways and exciting in some scary ways, but it's only really by understanding the interconnections between material science and technology, policy and cultural change, we've really got any chance of being successful. Thank you for listening.
Thank you very much. Another brilliant talk. Thank you very much, Phil. You invite good people, you get good talks. So I think we've already seen that twice, and I'm sure fans are going to be no slouch either. But when we come on to it, who's got some questions for Phil? Again, lots and lots of really interesting ideas. Yeah. I'm prepared to jump in and ask questions, but you don't want that. You really want you guys to.
Hi Phil, I'm Mark Midovnik from UCL.
Hi Mark.
Hi, great talk. I agree with everything you said. It just seems to me that we need some very it's very broad brush about how to move forward. But I guess one of the things that strikes me about the complexity of the challenges is just like it's so overwhelming. Where do we start to actually show that we've made progress in, like, how do we benchmark progress and set ourselves targets as a community and then sort of report back and say we've achieved this? Because it's so a lot of those things are so contingent on other industries. It's so hard, isn't it?
It is hard.
I feel like what I was going to ask you a question really is that case studies, it feels to me, and are the way to kind of really show we can do something. And I just give an example of one that's gone horribly wrong. Which is that we've talked about circularity in materials and complexity in electronic devices for years, like since 2018 at least, and yet we've got a new product onto the market, a disposable vape, right, which has replaced a reusable one. The medical community have sort of shrugged their shoulders and said, well, at least it's getting people off smoking. The young people are all using it under 18. That is probably harming their health terribly. They're being addicted to caffeine. But from a materials perspective, what we're seeing is electronic devices just being discarded onto the floor by the millions per week.
Yeah.
And that product is completely unregulated in the UK, as in terms of its circularity.
Yeah.
What do we do about that? Could we sort of say we're going to tackle that one problem?
Yeah, I think I agree with you that, there is a danger that you try and put in place the final solution and you become overawed by the complexity of the final solution. I think we shouldn't be doing it that way. And Royce has funded a few small projects, you may be aware of that. But I think we have to tackle it bit by bit, because the problem is it's an ecosystem. So even if you have the final solution, you may misjudge, as you talked about there, which you may get unintended consequences that you really didn't think about. So my view is we need to take it bit by bit. There are places where you can introduce what you perceive to be benefits and see how that goes. So I totally agree that it's actually about looking at smaller things and identifying where you can have an impact and tackling it that way, rather than relying on some big solution. Otherwise, we become overwhelmed by the complexity of the whole problem, I think.
Incredibly important, this, Phil. I must admit, I think that's a fantastically important conclusion about not seeking the answer. There ain't an answer, and if there is, we don't know what it is. No. And we're not going to find it. We're only going to find it by experimentation, doing things, some of which work a bit, some of which work a lot, some of which don't work at all, and gradually we've got a chance of evolving it. We've got to move fast, but we've got to do it bit by bit, as you said.
Yeah.